Good morning everyone. Myself Muskan from B.Sc Chemistry Honors second year. Today I am going to make an audio recording lecture for visual impaired students of physical chemistry by Dr. S.C. Khetarpal of chapter Thermodynamics 3. Work function Helmholtz free energy and Gibbs function Gibbs free energy. In addition to the various thermodynamic quantities like internal energy, work, heat, enthalpy, entropy, etc. discussed earlier, two more thermodynamic quantities used for frequently in the study of chemical thermodynamics are work function, also called Helmholtz free energy, and Gibbs free energy, collectively called free energy function. These are briefly described below. Number one, work function or Helmholtz function or Helmholtz free energy. This is usually denoted by the symbol A from the German word Arbeit, which means work and is defined by the equation A is equals to U minus Ts, where U is the internal energy of the function system, T is temperature, and S is the entropy. Since U, T, and S are the functions of the state of system only and do not depend upon its previous history, therefore A also must be a state function. In order to understand the physical significance of the work function, consider an isothermal change taking place at temperature T. Then A1 is equals to U1 minus Ts1 for the initial state, and A2 is equals to U2 minus Ts2 for the final state, where A1, U1 and S1 are respectively the value of work function, internal energy and entropy of the system in the initial state, and A2, U2 and S2 are the corresponding values in the final state. Therefore, increase in the function A accompanying the process will be given by A2 minus A1 is equals to U2 minus Ts2 minus U1 minus Ts1 is equals to U2 minus U1 minus T square bracket S2 minus S1. Delta A is equals to delta U minus T delta S, fourth equation, where delta U is equals to U2 minus U1 is the change in the internal energy of the system, and delta S is equals to S2 minus S1 in the change in the entropy of the system. Now, according to the definition of entropy change, we know that delta S is equals to Q reversible upon T, fifth equation. Further, according to the first law of thermodynamics as applied to an isothermal reversible process, we have delta U is equals to Q reversible minus W maximum. Minus sign before W has been used to indicate that the work has been done by the system during the change under consideration. Putting the value of delta S and delta U from equation 5 and 6 in equation 4, we get delta A is equals to Q reversible minus W maximum minus T dot Q reversible upon T minus delta A is equals to W maximum. Thus, for a process occurring at constant temperature, the decrease in the work function A is equal to the maximum work done by the system. In fact, it is for this reason that this thermodynamic quantity has been termed as work function. Although at one time it was called Helmholtz free energy. Number 2, Gibbs function यानी कि Gibbs free energy. This is usually denoted by G and is defined by the equation G is equals to H minus Ts, where H, T and S are the heat content, enthalpy, temperature and entropy of the system respectively. As before, since H, T and S are functions of the state, therefore G is a function of the state of the system only. Hence, for the isothermal process occurring at temperature T, we can write G1 is equals to H1 minus Ts1 for initial state, G2 is equals to H2 minus Ts2 for final state. G2 minus G1 is equals to square bracket H2 minus Ts2 minus square bracket start H1 minus Ts1 square bracket close is equals to H2 minus H1 minus T square bracket start H2 minus H1 square bracket close. Delta G is equals to delta H minus T delta S, where delta G is equals to G2 minus G1 is the change in Gibbs free energy of system. Delta H is equals to H2 minus H1 is the enthalpy change of the system. Delta S is equals to S2 minus S1 is the entropy change of the system. The physical significance of Gibbs free energy may be obtained as follows. At constant temperature T, delta S is equals to Q reversible upon T by definition of entropy change. T delta S is equals to Q reversible. At constant pressure P, delta H is equals to delta U plus P delta V by definition of enthalpy change. Substituting the value of T delta S and delta H from equation 12 and 13 in equation 11, we get delta G is equals to delta U plus P delta V minus Q reversible is equals to delta U minus Q reversible plus P delta V. According Now, according to first law of thermodynamics, delta U is equals to Q reversible minus W max. Minus sign before W indicates that work is done by the system, or delta U or Q reversible is equals to minus W max. Substituting the value in is equation 14, we get delta G is equals to minus W max plus P delta V. Minus delta G is equals to W max minus P delta V. But P delta V is the work of expansion done by the system corresponding to the increase in value delta V. Hence, W max minus P delta V stands for the maximum work done, work other than the work of expansion. This is called the maximum net work available from the process. Hence, we conclude that for a process occurring at constant temperature and constant pressure, the decrease in Gibbs free energy is equal to the maximum net work obtainable from the process, that is the total work minus the pressure, volume or work of expansion. It is because the change in G is a measure of the useful work done that G has been called as the free energy. It may be further mentioned hence here that it is customary to refer to Gibbs free energy simply as free energy. The designing Gibbs or Helmholtz is added only when necessary for clarity. Variation of Helmholtz function or work function with temperature and volume. The work function is given by the equation A is equals to U minus Ts. Complete differentiation of equation gives dA is equals to du minus Tds minus STT. By definition of entropy change, we know that ds is equals to del Q reversible upon T. Further, from first law of thermodynamics, we have del Q reversible is equals to du minus small change W, and if the work is restricted to the work of expansion only, minus partial W is equals to PdV. Putting this value in equation 4, we have partial Q reversible minus du plus PdV. Putting this value in equation 3, we get ds is equals to du plus PdV upon T. Tds is equals to du plus PdV. Putting this value in equation 2, we obtain dA is equals to du minus du plus PdV minus SdT is equals to minus PdV minus SdT. If temperature is kept constant, Tt is equals to 0. Equation 8 from form takes the form Ta at constant temperature is equals to minus PdV at constant temperature. Del A upon del V at constant temperature is equals to minus P. If volume is kept constant, dV is equals to 0. Equation 8 becomes dAV is equals to minus SdT at constant volume, del A upon del T, partial A upon partial T is equals to minus S. Equation 9 and 10 gives the variation of work function with temperature and volume. The change in work function for a complete process under isothermal condition can be calculated as follows. For an infinitesimal change under isothermal condition, equation 9 may be written as dA at constant temperature is equals to minus PdV. For a complete process under isothermal condition, when the volume changes from V1 to V2, we will have del AT is equals to minus V1 to V2 PdV. Putting PV is equals to nRT, that is P is equals to nRT upon V. For n moles of an ideal gas, we get del AT is equals to minus nRT of V1 to V2 dV. Del AT is equals to minus nRT ln V2 upon V1. Del AT is equals to minus W max. This is the same result as derived earlier in equation 7. Variation of Gibbs function, free energy with temperature and pressure. The free energy is given by the equation G is equals to H minus Ts by definition of enthalpy. H is equals to U plus PV. Putting this value in equation 1, we get G is equals to U plus PV minus Ts. Complete differentiation of the equation gives dG is equals to du plus PdV plus VdP minus TdS minus SdT. ds is equals to del Q reversible upon T is equals to du plus PdV upon T. TdS is equals to du plus PdV. Substituting this value in equation 4, we obtained dg is equals to du plus pdv plus vdp minus du plus pdv minus sdt is equals to vdp minus sdt. dg is equals to vdp minus sdt. Equation 6. This is an important expression which gives the change in free energy with change in pressure and change in temperature is a reversible process. Total differential equation, if temperature is kept constant, dt is equals to 0. Equation 6 takes the form dgt is equals to vdpt. Del g upon del p at constant temperature is equals to v. B, if pressure is kept constant, dp is equals to 0. Equation 6 become dgp is equals to minus s dtp. Del g upon del t at constant pressure is equals to minus s. Equation 8 and 9 give the variation of free energy with pressure and temperature. The change in free energy for a complete process under isothermal conditions can be calculated as follows. For an infinitesimal change under isothermal condition, equation 7 may be written as dg at constant temperature is equals to vdp. Equation 10. For a complete process under isothermal condition, when the process changes from P1 to P2, we will have del G at constant temperature is equals to vdp P1 to P2. Putting PV is equals to nRT, that is V is equals to nRT upon P for n moles of an ideal gas. We get del G at constant temperature is equals to limit P1 to P2 nRT upon P dP is equals to nRT limit P1 to P2 dP upon P is equals to nRT ln P2 upon P1. Equation 12. Further, for an isothermal process, P1 V1 is equals to P2 V2 or P2 upon P1 is equals to V1 upon V2. Substituting this value in equation 12, we get del G at constant temperature is equals to nRT ln P2 upon P1 is equals to nRT ln V1 upon V2. Equation 13. This is the same expression as equation 13 for change in work function. Thus, del GT is equal to del AT. This appears to be in contradiction with the result discussed earlier. However, it may be understood clearly that the equality holds good for an ideal gas but not in general. Criteria for feasibility of a process. As already discussed, the net entropy change for the combined system and the surrounding delta S system plus delta S surrounding can be taken as a criteria for the feasibility of the spontaneity of a process. The result arrived at were number 1. If delta S system plus delta S surrounding greater than 0, the process is irreversible. That is, it is spontaneous as feasible. Number 2, if delta S system plus delta S surrounding is equals to 0, the process is reversible, that is, the system is in equilibrium. The above two result may be combined and put in the form delta S system plus delta S surrounding is greater than equal to 0, that is equation 1, where the sign greater than refers to an irreversible process, that means spontaneous process, and the sign equal to is for a reversible process, that is for a state of equilibrium. The above criteria, however, require knowledge of both delta S system and delta S surrounding, which is not convenient. Hence, a number of other criteria which require to knowledge of the change in some thermodynamic quantities of the system, only one preferred. These may be derived as follows. For an infinitesimal process, the above criteria may be written as ds system plus ts surrounding is greater than equal to 0. That is equation 2, where the sign greater than stand for irreversible process and the sign equal to stand for reversible process. If the surrounding lose heat del Q reversibly and isothermally at the temperature T which may be absorbed by the system reversibly or irreversibly, then dS surrounding is equals to minus del Q reversible upon T, that is equation 3. Further, according to first law of thermodynamics, del Q reversible is equals to du plus PdV, that is equation 4. Substituting this value in equation 3, we get dS surrounding is equals to minus du plus PdV upon T, that is equation 5. Substituting this value in equation 2, we get dS system minus du plus PdV upon T, that is greater than equal to 0. TdS minus du minus PdV, that is greater than equal to 0, that is equation 6. TdS is greater than equal to du plus PdV, where ds stand for the entropy change of the system and the subscript system has been omitted. Equation 6 is the basic equation which leads to a number of criteria for predicting the feasibility of a process. In this equation, the sign equal stand for the reversible process and the sign greater for the irreversible process. From equation 6, the various criteria may be deduced as follows. Number 1, in terms of entropy change of the system, if the entropy, internal energy and the volume of the system are kept constant, du is equals to 0 and dv is equals to 0. Then from equation 6th we have TdS uv greater than equal to 0, then ds uv greater than equal to 0, that is equation 7, where the sign equal is for the reversible process and the sign greater for irreversible process. The subscript u and v indicate the constancy of these properties. Number 2, in terms of internal energy change of the system, if the entropy and the volume of the system are kept constant, that means ds is equals to 0 and dv is also equal to 0. Then equation 6th become 0 is greater than equal to dus or v. Dus or v is less than equal to 0, where the sign equal stand for the reversible process and the sign less than for the irreversible process. This implies that if a process under constant condition of entropy and volume is accompanied by a decrease of internal energy, the process is irreversible. If no change in internal energy take place, the process is irreversible. The process is irreversible. Number 3, in terms of enthalpy change of the system, by definition of enthalpy H, we know that H is equals to U plus PV. Complete differential of this equation gives dH is equals to du plus PdV plus VdP, or du plus PdV is equals to dH minus VdP. Putting this value in equation 6, we get TdS is greater than equal to dH minus VdP. If entropy and pressure of the system are kept constant, ds is equals to 0 and dp is equals to 0, so that 0 is greater than equal to dh s or p. dh s p less than equal to 0, equation 9, where the sign equal to refers to the reversible process and the sign less than refer to irreversible process. Number 4, in terms of change in work function of the system, by definition work function is given by work function a is given by a is equals to a is equals to u minus ts. Differentiating this equation completely, we get dA is equals to du minus tds minus s dt. Tds is equals to du minus s dt minus dA. Putting this value in equation 6, we get du minus s dt minus dA greater than equal to du plus pdv, minus s dt minus dA greater than equal to pdv, s dt plus dA less than equal to minus pdv. If temperature and volume of the system are kept constant, that means d is equals to 0 and dv is also equal to 0, so that we have dATV less than equal to 0, that is equation 10, where as usual sign equal is used for reversible process and sign less than for the irreversible process. Number 5, in terms of free energy change of system, by definition free energy is given by G is equals to H minus Ts. Further, H is equals to U plus PV, therefore G is equals to U plus PV minus Ts. Complete differential of this equation gives dc is equals to du plus pdv plus vdp minus tds minus sdt. de plus pdv is equals to dg minus vdp plus tds plus sdt. Putting this value in equation 6, we get tds is greater than equal to dg minus vdp plus tds plus sdt. 0 is greater than equal to dg minus vdp plus sdt, or dg minus vdp plus sdt is less than equal to 0. If pressure and temperature of the system are kept constant, dp is equals to 0 and dt also equal to 0, so that we obtain dg pt less than equal to 0, that is equation 11. whereas before the sign equal refer to reversible process and sign less than is refer for irreversible process. The criteria in terms of free energy change is most significant because most of the processes take place at constant temperature and pressure. This criteria implies that number 1, if dgpt less than equal less 0, the process is irreversible, that is it is feasible. Number 2, if dg at constant p and t is equals to 0, the process is irreversible, the system is in equilibrium. If dg pt greater 0, the process does not occur, that is it is not feasible. Limitation of the criteria for spontaneity. Note doubt, the various criteria discussed above are helpful in predicting the spontaneity of a process, but they do not tell about anything about the following. Number 1, the extent to which reaction take place. Number 2, the rate at which reaction proceed. Number 3, the mechanism by which the reaction proceeds. Advantages of free energy criteria over entropy change. An important advantage of free energy criteria over entropy criteria lies in fact that the former requires free energy change of the system only at constant P and T and is not concerned with what is happening to the surrounding, whereas the later, that is entropy change criteria, requires the total energy change of the system and surrounding, that is for the process to the spontaneous, delta S total is equals to delta S system plus delta S surrounding must increase. Gibbs-Helmholtz equation. The Gibbs free energy G is given by the equation G is equals to H minus Ts, that is equation 1. Hence, for an isothermal process, we can write G1 is equals to H1 minus Ts1 for initial state, that is equation 2. G2 is equals to H2 minus Ts2 for the final state, that is equation 3. Subtracting equation 2 from equation 3, we get G2 minus G1 is equals to H2 minus Ts2 minus square bracket start H1 minus Ts1 square bracket close. Square bracket H2 minus H1 minus T square bracket H2 S2 minus S1. Delta G is equals to delta H minus T delta S, equation 4. Delta G is equals to G2 minus G1 is the change in the free energy of the system. Delta H is equals to H2 minus H1 is the change in entropy of the system. Delta S is equals to S2 minus S1, that is the in the entropy change of the system. Taking up equation 1 again and putting H is equals to U plus PV, we get G is equals to U plus PV minus Ts, that is equation 5. Differentiating this equation completely, we get dG is equals to du plus PdV plus VdP minus TdS minus SdT, that is equation 6. ds is equals to Q reversible upon T by definition of entropy change is equals to du plus PdV upon T, because Q reversible is equals to du plus PdV by the first law of thermodynamics. TdS is equals to du plus PdV. Substituting this value in equation 6, we get dG is equals to VdP minus SdT. If pressure is kept constant, dP is equals to 0, so that we have dG at constant P is equals to minus SdT at constant P. Del G upon del T at constant P is equals to minus S. That is equation 8. For the initial state, dG1 del G1 upon del T at constant P is equals to minus S1. For the final state, del G2 upon del T at constant P is equals to minus S2. Subtracting equation 8 and from 9, we get del G2 upon del T minus del G1 upon del T at constant P is equals to minus S2 minus square bracket minus S1 is equals to minus S2 plus S1 is equals to minus square bracket start S1 to minus S1 square bracket close is equals to minus delta S. Or it may be written as del G2 minus G1 upon del T at constant pressure is equals to del minus del S or del delta G upon del T at constant P is equals to minus del S, equation 10. Substituting this value of delta minus delta S in equation 4, we get del G is equals to del H plus T square bracket del delta G upon del T at constant P, that is equation 11. This is the most common form of Gibbs-Helmholtz equation. Starting with the expression for the work function, that is A is equals to U minus Ts, and proceeding exactly in a similar manner as above, the following analogous expression can be derived. Delta A is equals to delta U plus T square bracket del delta A upon del T square bracket close at constant V, that is equation 12. This is another form of Gibbs-Helmholtz equation. Further, sometimes Gibbs-Helmholtz equation is put still in another form, which is derived from equation 11 as follows. Dividing equation 11 throughout by T square, we get del G upon T square is equals to del H upon T square plus 1 by T del delta G upon delta T at constant P equation 30, or 1 by T square bracket start del delta G upon del T at constant P minus delta G upon T square minus is equals to minus del H upon T square, or del square bracket del delta G upon T upon del T at constant P is equals to delta H upon T square, equation 14. It may be noted that all form of Gibbs-Helmholtz equation involve quantities like delta G and delta H, or delta A and delta U, which are the state function and do not depend upon the path followed. Hence, Gibbs-Helmholtz equation is a general equation applicable to reversible as well as irreversible processes. Application of Gibbs-Helmholtz equation. One of the application of the Gibbs-Helmholtz equation, expression 11, is that knowing the free energy change at any two different temperature, the enthalpy change accompanying the process can be calculated. However, the most important application of the Gibbs-Helmholtz equation is in the study of galvanic cells or electrochemical cell, which is briefly explained below. When a redox reaction, example Zn plus CuSO4 मिलकर बनाएंगे, ZnSO4 plus Cu is allowed to take place in a single beaker, heat is evolved. Earlier it was believed that when the same reaction is allowed to take place in an electrochemical cell, the electrical energy produced was equivalent to the heat evolved. However, later on it was found that is Gibbs and Helmholtz by stating that the electrical energy produced was equal to decrease in the free energy minus del G accompanying the cell reaction. They pointed out that if N is the number of electrons given out by one of the electrode, example for zinc Zn2 positive plus 2 electron, N is equals to 2, or taken up the other electrode, example Cu2 positive plus 2 electron, that is Cu, N is equals to 2, then the quantity of electricity produced is equals to Nf Faradays, where F is equals to 1, or Faraday is equals to 96500 coulombs. If E is the EMF of the cell, then electrical energy produced by the cell is equals to Nfe. Therefore, decrease in free energy minus del G is equals to Nfe. Substituting this value in the Gibbs-Helmholtz equation, equation 11, we get minus Nfe is equals to delta H plus T square bracket del minus Nfe upon del T at constant P. Nfe is equals to minus del H plus T and F del E upon del T at constant P. Thus, knowing the temperature coefficient of the EMF of the cell, that is del E upon del T at constant P, delta H can be calculated if E is known or vice versa. If evidently the electrical energy produced, Nfe is equal to the heat evolved minus del H only when del E upon del T at constant P is equals to 0. Nernst heat theorem. W. Nernst 1906 made a detailed study about the variation of entropy change del H and free energy change del G. If a system with a decrease of temperature, the result thus obtained is called Nernst heat theorem and is briefly described below. According to Gibbs-Helmholtz equation, delta G is equals to delta H plus T del G upon del T at constant P. From this equation, it is evident that at the absolute zero, that is when T is equals to 0, delta G is equals to delta H unless delta G upon del T is infinite. However, Nernst observed that as constant temperature is lowered towards absolute zero, the value of del G upon del T decreases and then approaches zero asymptotically. This means that delta G and delta H are not only equal at absolute zero, but the values approach each other asymptotically in the vicinity of the temperature. This result is known as Nernst heat theorem. Mathematically, it may be expressed as limit T tends to 0 d delta G upon dt is equals to limit T tends to 0 d delta H upon delta T is equals to 0. That is equation 1. Graphically, the result may be represented as shown. Delta G has been shown as greater than delta H as at temperature away from absolute zero. However, the reverse is also possible because delta G by del T can be both positive or negative, but we know that delta G upon del T at constant P is equals to minus S, and delta H upon delta T at constant P is equals to delta Cp. Combining these result with equation 1, we get limit H tend to 0, delta S is equals to 0, and limit H tend to 0, delta Cp is equals to 0. That is equation 2. Since gases do not exist at the absolute zero, this means that the heat theorem is not applicable to gases. Similarly, it can be found to be inapplicable to liquid also. Thus, Nernst heat theorem is applicable to solid only. Third law of thermodynamics. The result of the Nernst heat theorem led to enunciate a generalization which has been called as the third law of thermodynamics. In other words, the third law of thermodynamics follows from the result of Nernst heat theorem as briefly explained below. According to Nernst heat theorem, delta Cp approaches 0 at 0 Kelvin. This implies that at 0 Kelvin, the heat capacities of the reactants and product become equal because delta Cp is equals to Cp product minus Cp reactant. It seems most probable that at 0 Kelvin, all substances have the same heat capacity. On applying quantum theory to the heat capacities of solid, it is found that heat capacity of solid tend towards 0 at 0 Kelvin. Thus, Nernst heat theorem leads to the following result. Limit h tends to 0, Cp is equals to 0. Also from Nernst theorem, limit h tends to 0, delta S is equals to 0. Proceeding exactly in the same way as above, it may conclude that all solids have the same entropy but all at absolute 0 of temperature, and it tends towards 0 at absolute 0 of temperature, that is limit h tends to 0, S is equals to 0. This generalization is known as third law of thermodynamics. It may be stated as under: the entropy of the all perfectly crystalline solid may be taken as 0 at the absolute 0 temperature. In a broader sense, the law is usually stated as follows: every substance has finite positive entropy, but at the absolute 0 of temperature, the entropy may become 0, and in fact, it does become 0 in case of perfectly crystalline solid. Like the first and the second law, this law is also a generalization based upon the experience, and there is no direct proof for this law. However, the law has been verified in a number of ways, and there is no doubt about the validity of the law. It is important to note that third law of thermodynamics does not state that entropies are 0 at T is equals to 0. It merely states that all perfectly crystalline solids have the same entropy at T is equals to 0. Choosing a common value of as 0 is only a matter of convenience. Important to the third law, evolution of absolute entropies. The importance of the third law lies in the fact that it helps in the calculation of the absolute entropy of element or chemical compound at any desired temperature. This may be illustrated as follows: the infinitesimal entropy change is given by ds is equals to del q by t, first equation, but Cp is equals to del q by dt, so that del q is equals to Cp dt. Substituting this value in equation 1, we have ds is equals to Cp dt upon T. Hence, the entropy change of a substance when its temperature changes from absolute 0 to temperature T will be obtained from the equation ds s limit s is equals to s0 to s is equals to s is equals to limit h is equals to t0 to t is equals to t Cp dt upon T, or st minus s naught is equals to limit 0 to t Cp dt upon T, equation 2, where s naught is the entropy of substance at absolute 0 and st is the entropy of substance at temperature T. Now, according to third law of thermodynamics, s naught is equals to 0, st is equals to 0 to T, Cp dt upon T is equals to 0 to T Cp d ln T, that is equation 3. Thus, the entropy S of the substance at temperature T can be calculated from the measurement of heat capacity Cp at a number of temperature between 0 Kelvin to 7 K Kelvin. The integral in equation 3 can be evaluated by plotting Cp versus ln T, that is 2.303 log T, or Cp by T versus T, and then measuring the area under the curve between T is equals to 0 or T. Thus, the evaluation of entropy requires the measurement of heat capacity at different temperature down to 0 Kelvin. However, a problem arises with the measurement of heat capacities at low temperature less than 15 Kelvin. For example, in plot given the above, the heat capacity along the curve BC are experimental value, the point B corresponding to the lowest temperature up to which the experimental value can be determined accurately. To get the complete area under the curve from T to 0 Kelvin, extrapolation of the curve is done as shown by the portion BA of the curve. The value corresponding to extrapolated portion is usually found by applying Debye third power law for the heat capacities of solid at low temperature. through Cp is equals to AT cube, equation 4, where A is an empirical constant. If B corresponding to temperature T1, that is the lowest temperature up to which the heat capacity can be measured experimentally. C correspond to temperature T, that is temperature at which entropy is to be determined. And remembering that A correspond to 0 Kelvin, integral given in equation 3 can be split into two parts as follows. St is equals to limit 0 to t1 Cp upon t dt plus limit t1 to t Cp t dt. Equation 5. The value of the first integral can be found by substituting the value of Cp from equation 4. That is, we have 0 to t1 Cp upon t dt is equals to 0 to t1 At cube upon t dt is equals to 0 to t1 At square dt is equals to At1 cube upon 3. Hence, equation 5 becomes St is equals to At1 cube upon 3 plus T1 to T Cp upon T dt. Equation 6. Further, as Cp is equals to At cube, therefore At1 cube upon 3 is equals to 1 by 3 Cp at T1. This means that the entropy change from 0 K to T1, that is St1, is equal to 1/3 of the value of Cp and T1. Hence, equation 5 can be simplified further to the form St is equals to 1 by 3 Cp at T1 plus T1 to T Cp T upon T dt. Equation 7. It is important to remember that the calculation as described above are applicable only at a solid involving no polymorphic change, that is, a change from one crystalline form to another between 0 degree to T degree Kelvin. If some polymorphic change is evolved in the range, the entropy of transition delta TRH upon TTR, where delta TRH is the molar heat of transition and delta TTR is the transition temperature, will have to be included in the value calculated above. For liquid and gaseous substance, the total absolute entropy of the substance at the given temperature will be sum of all the entropy change which the substance has to undergo in order to reach that particular state starting from the crystalline solid at absolute zero. Thus, if a substance is gaseous at 1 atmospheric pressure and 25 degrees Celsius, the entropy of the gas at 25 degrees Celsius, which will be the sum of following entropies involved at different stages. Number 1. The entropy of heating the crystalline solid from T is equals to 0 to T is equals to T at the melting point of fusion temperature. Number 2, the entropy of fusion or fusion delta FH upon TF, where delta FH is latent heat of melting of fusion. Number 3, the entropy of heating the liquid from TF to TB, the boiling point. Number 4, the entropy of vaporization delta VH upon TB, where delta VH is the latent heat of vaporization. Number 5, the entropy of heating the gas from TB to 25 degrees Celsius, that is 298 Kelvin. Thus, the complete expression for the calculation of entropy at temperature T may be written as St is equals to 0 to Tf Cp as d ln T plus delta Fh upon Tf plus limit at Tf to Tb Cpl d ln T plus delta Vh upon Tb plus limit h Tb to T Cpg d ln T. Equation 8. A. If the substance is solid at temperature T, only first term is to be taken with Tf is equals to T. B. If the substance is liquid at temperature T, the first three terms are to be taken with Tb is equals to T. C. If the substance is gaseous, full equation is to be used. If the solid involves a polymorphic transition, another term delta TRH upon TTR has to be inclined in the above expression as already explained. Further, the first integral should be made up of two parts as given by equation 5, 6, 7. The various entropy changes that occur where the temperature of substance rise from absolute zero may be represented. Test of the third law of thermodynamics. Number 1, by calculation of equilibrium constant. The equilibrium constant K is related to standard free change energy delta G naught according to the equation minus del G naught is equals to RT ln K. Equation 1. The standard free energy change is related to the standard enthalpy change delta H naught and standard entropy change delta S naught according to the equation delta G naught is equals to delta H naught minus T delta S naught. Equation 2. Putting the experimental value of delta H and calculated value of delta S naught using the absolute value of entropy is obtained from the third law of thermodynamics and applying the relation delta S naught is equals to summation S naught product minus summation S naught reactant. Delta G naught can be calculated for a reaction. Putting this value of delta G naught in equation 1, the equilibrium constant K can be calculated. It is found that for a number of reaction, the value of equilibrium constant as calculated above comes out to be in close agreement with the experimental value. Number 2, by comparing with entropies calculated from satisfaction mechanism. The absolute entropies calculated on the basis of third law are found to be in complete agreement with those calculated using statistical mechanism. Number 3, by proving that different allotropic form of substance have equal entropies at absolute zero. Orthorhombic sulfur S alpha changes into monoclinic sulfur S beta at the transition temperature at 369 Kelvin. The enthalpy of transition delta HU TR is found to be minus 402 joules per mole. Hence, molar entropy of transition will be given by delta TR S is equals to S alpha minus S beta is equals to delta TRH upon delta T TR is equals to minus 402 joule per mole upon 369 Kelvin is equals to minus 1.09 joule per mole per Kelvin. That is equation 3. The individual entropy of the two form can also be calculated by measuring their heat capacities from T is equals to 0 to T is equals to 369. It is found that S alpha is equals to S naught beta plus 337 joule per Kelvin per mole. S beta is equals to S naught beta plus 38 joule per Kelvin per mole. Hence, at the transition temperature, delta TRS is equals to S naught alpha minus S naught beta minus 1 joule per Kelvin per mole is equation 4. Comparing equation 3 and 4, we get S naught alpha minus S naught beta is equals to 0, S naught alpha is equals to S naught beta. The element is in perfectly crystalline form are arbitrarily ascribed a value of 0 for the entropy of absolute 0. Then all perfectly crystalline compound will also have zero entropy of at 0 Kelvin, keeping in mind the definition of entropy of formation of a compound, residual entropy. As explained above, entropy can be determined by applying third law of thermodynamics. These can also be calculated from statistical mechanism or from spectroscopic data. It is found that in most of the cases, the agreement between the third law entropy and those calculated from statistical mechanism is very fair. However, in some cases, the experimental value as found from third law is found to be less than the calculated value. For example, standard entropy found from third law and calculated from statistical mechanism for CO and N2O are given below. The lowest value of third law entropy and explained on the basis that at T is equals to 0 Kelvin, the crystals of these substances are not perfect. That is, there is some disorder present in the solid even at T is equals to 0 Kelvin. The entropy which the crystal of a substance has at T is equals to 0 Kelvin is called residual entropy. Origin of residual entropy. To understand the origin of residual entropy, let us consider a crystal made up of AB molecule where A and B are similar atoms, so that the molecule has very small electric dipole moment. These molecules can adopt different orientations such as AB, 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 AB or AB, AB, BA, BA, AB moment. These arrangement or many other random arrangement that the molecule can adopt have very little difference of energy. Thus, there is residual disorder and hence there is residual entropy at 0 Kelvin. Calculation of residual entropy. Residual entropy can be calculated by applying Boltzmann formula via through S is equals to K L and W, where W represents the number of possible orientation of the molecule that are equal probable, that is have nearly the same energy, and hence W is called thermodynamic probability, and K is Boltzmann constant. A few examples are given below. Number 1, residual entropy of CO. Suppose a sample consists of n molecule of CO. Now, as each molecule can have two orientation that are equally probable, that is CO, CO, OC, CO, OC, OC. Therefore, some energy can be achieved in 2 n different ways. W is equals to 2 to the power n. Hence, S is equals to K ln 2 raised to power n is equals to K n ln 2. If 1 mole of the sample is taken, Kn is equals to R, then S is equals to R ln 2 is equals to 2.303 R L log 2 is equals to 2.303 into 8.314 into 0.3010 joule per Kelvin per mole is equals to 5.85 joule per Kelvin per mole. Number 2. Residual entropy of FClO3. FClO3 molecule can have 4 possible orientation with a nearly same energy. Hence, residual entropy is S is equals to R ln 4 is equals to 2.303 R log 4 is equals to 2.303 into 8.314 into 0.6021 is equals to 1.5 joule per Kelvin per mole. In general, if a molecule can adopt P possible orientation at T is equals to 0, which have nearly the same energy, the residual molar entropy will be SR is equals to R ln P. Thank you.